Hi, everyone. Welcome to this afternoon. So here we are going to talk a little bit more about some of the specific terms that Charlotte, Ankitha, and Kaiki used this morning, and also go over some math. We're going to start with that. Just to start, uh, here is on the left-hand side, we have what molecular diffusion looks like. But when we have turbulence, crazy things happen. Wow. So now, if we want to zoom in to a very small scale, and now we want to ask, what is happening on these scales? All right. So to talk about that, we're going to start with the variance for the velocity and do the variance for the velocity and energy system. So starting with the Navier-Stokes, we have the mean and the turbulent Navier-Stokes equations. This is exactly what Andrea did yesterday. This is index notation. If you guys got a chance to review Andrea's notes, that's awesome. Just very quick, whenever you see an index, you are implicitly summing over all of the possible X, Y, and Z. Usually it's okay. So on the top one, you might not recognize this last term, but we are just going to be assuming that the only thing density depends on is temperature. It makes a lot of the math easy. And yeah, what's that? Right, it's just that's the mean part, that's the turbulent part. Does that have anything else? All right, cool. So yeah, this is the equations for velocity. But now we want to actually talk about dissipation. And dissipation is a measurement of energy over time. So to do that, we got to start with calculating the kinetic energy, which we can do with, you recognize these from physics. We have capital E, big E for the mean flow, and we have little e for the little fluctuating flow. Okay, cool. So this is the mean energy equation. Here are what each of the terms represent. We start with the material derivative on the left-hand side, and then we have the transport. Andrea will talk more about what each of these terms means. The one that I want to point out here is that for the mean flow equation, that viscous dissipation term is negligible. And you can see that from just doing a scale analysis. If I calculate, should I do it out? No, I'm going to do it out. So if you have viscosity, and then I'm just going to write out the scales for the dissipation term. So you have viscosity, and then U squared over L squared. And let's say I want to compare it to one of these other terms. Let's pick the shear loss one. So then for the shear loss, we have a U squared again, and then U over L. So let's cross stuff out, and then do some fun things. We wind up with viscosity over UL. And if you've heard me talk yesterday, what is that? What does it look like? Oh my God, it looks like a Reynolds number, specifically 1 over the Reynolds number. So if we are already talking about turbulence, we know that Reynolds number is big, and as a result, this has to be small. And then here is the turbulent energy part. It has pretty much most of the same terms. The one thing that you might notice is that they share a term in common. So both of them have this like Reynolds stress times the shear of the mean flow term. So for the mean flow, we will call that shear loss because that will be energy lost due to this process. And it is gained by the turbulent part of this equation. And in this case, now this last viscous term is important. It is no longer small. And to see why, we can look at the exact same thing. Earlier, this view was representing the mean flow, but now that it's the fluctuating flow, it's really, really small. So this winds up going the other way, and this top viscosity term becomes a lot more dominant. So yeah, here are these basic equations, and now Andrea will tell you more about each of these terms.
I just want to note that if you were curious about how we got to this point from the Navier-Stokes equations, it is in the lecture notes. I have a fairly detailed analysis of how we get each term. If you want to go through the math, and I'll be saying like little e, I'll be calling TKE or turbulent kinetic energy, kind of interchangeable with E. And the top one, big E, is mean kinetic energy. So following on from what Helen was saying, I'm going to go term by term, and I'm going to start with the shear production term we're looking at the terms in the turbulent kinetic energy equation because that's the only one we are caring about right now. But we're going to start with this term that is shared between the mean and the turbulent kinetic energy, which is that shear production term, which I have here. What shear production is it's the gain to turbulent kinetic energy from the mean flow via mean velocity gradients. So essentially, in a similar way to how we were talking before about energy going down scales, this is essentially a representation of that, where you have a transfer between your mean flow and your turbulent flow. This is an example just of some what's called Helmholtz billows. Basically, you can just see that they go from larger kind of scales to, once they collapse a little bit, it gets a little smaller. So you just things going from larger scales to smaller scales. I forgot how much we were going to talk about that before I made this slide, so you guys already understand this pretty well. And one way to think about that visually is, as Charlotte was already saying, you get energy from some kind of mean flow or tides or whatever it is. Various processes happen, which we'll go into more as the course progresses, but that's not really the details of this lecture right now. That energy is then going to progress through from, different sizes of eddies, say, and then it'll go down to eventually some small scale where you get viscous dissipation and loss to heat. So the shear production is essentially saying, okay, well, what are the things that are creating these eddies, which will then kind of get from which the energy will cascade into smaller scales. Buoyancy production is a very similar thing, but now it is driven, so instead of having shear be driving the eddies that you're seeing, now it's density fluctuations, or in this case, temperature variations, because I deliberately wrote this equation with T instead of rho, which would become clear when we talk about the temperature variance equation. But obviously, temperature isn't the only thing defining density. We're just making that assumption for right now. But basically, in the same way that you can have eddies and various different larger scale processes driven by shear, you can have them driven by buoyancy. It's kind of like what Kaiki was saying with his shear and strain discussion at, what was it, yesterday? And so again, it's a similar idea. It's how the turbulent kinetic energy equation is gaining TKE. Transport is a bit of well, it's simultaneously obvious and a little confusing for people. So when you think about how much, that TKE budget is a budget, right? So things are coming in and out, as well as being created, as well as being dissipated, right? So we've talked about the things that are being created. That's how the TKE is growing. There's also parts of the TKE that are just moving around, right? So if you're looking at a given parcel of water, there can be TKE coming in and out, for example, because you're trying to make a budget around some control volume. So inside the parentheses, you have a few different terms: diffusion of energy across some boundary, advection, pressure forcing. All of these things will cause energy to kind of move across a surface, or one boundary. And then you need to take the derivative of that in whatever dimension that you're looking at your equation in. So say it's X that you're looking at. That ddxj that's doing the difference between all of these terms is basically allowing you to get a net transport. So it's in minus out, right? So that's just to understand kind of what that term means. You're getting your kind of, some of these seem like double derivatives, some of them not, but the reason for that is that they're all kind of within this ddxj that is taking into account the fact that you have to balance in and out. And finally, we have our loss term. So if we gain energy from the mean flow and we also have energy that can move around, we can also have energy kind of going away. And how does that happen? In this case, via this dissipation. So at small enough scales, TKE is transformed into heat via frictional effects. And so we call that the rate of TKE dissipation, or epsilon, as you've no doubt seen it before. Viscous dissipation here is defined as that new DUI, DXJ, DUI, DXJ term. And so that was in the equation. You just pull it right out from the equation. But that epsilon is going to be important because that's basically this part. That's how much of the energy you can assume to be lost to heat. And that's useful to us because we need to consider, I don't know. Okay. You know, if you make the assumption that like you have the same amount of energy going to every single scale all the way through, if you know how much is being lost here, then you know how much is kind of going at each different scale. Obviously, Charlotte just talked about how that's not necessarily super valid or accurate, but it's an assumption that you can make, and we will make for a lot of the instruments and theory that progresses forward. So still talking about this viscous dissipation term, if we assume isotropy, which means basically you assume that all the motions, the small scale motion, these U primes, U prime, B prime, W prime, the little I is saying that it can go in quicker. Basically, you're saying that there's no bias towards any one direction. So you don't have to worry about things being weighted more to like one side of your tensor. For example, if you're looking at your energy, like du dx versus du dy, you have a clear, so basically what it means is that du dx and dv, dy, and dw, dz are all the same. And then the off diagonal terms have a predictable relationship with them. Again, if you look at the notes, we can go into the details more, and I'm super happy to do that. But if you assume this isotropy, you assume that there's this clear relationship between the different i's and j terms of your epsilon, you can find a way to basically rewrite this in terms of just one of these terms. So instead of DUI, DXJ, DUI, DXJ, and then you have to have the instantaneous shear in every direction. Now, if we have the instantaneous shear just in like U and X, you have a way of calculating what epsilon is. Or in the ocean, we tend to prefer this last one because du dz is pretty straightforward, and that like you drop something down from a profiler and it's wiggling on its way down. So now you have du dz basically measured. And so if you can make an isotropic assumption and you have this equation for epsilon, now you can basically assume that your epsilon is equal to 15/2 nu times this quantity, which is actually measurable for us, instead of measuring all of the different gradients as well. And if we have time, I will explain them after that. Go for it.
So kind of very similar logic. We can do the same thing for temperature and solve for fluctuations in temperature. So in this case, we're thinking of a quantity that all comes to the variance. This quantity, yeah. So and you get pretty much the same processes that we had talked about. So you have a term that's kind of their rate of change, as well as kind of the effective influences. We have a term that's production from the mean gradients. So this is sort of you have a mean temperature gradient, and then you have these turbulent fluctuations that then drive the production of turbulence. We can also kind of transport these temperature fluctuations around, and similarly also drive the dissipation of temperature gradients. And in this case, as we've been talking about in many different ways, what turbulence does, as we've kind of talked about in our first section, is it creates these gradients across which diffusion can occur. That is how the temperature variance dissipates. So all of these processes create kind of gradients in temperature, or transport it, and then we get that dissipation. And it follows a very similar structure to the momentum gradients equation. And like Andrea explained, the math is a little bit simpler here. So if you assume isotropy, you can kind of assume again that the temperature gradients are the same in all three directions, and just look at one change in temperature and depth, take that to be the same for all other dimensions, and then you can get an equation for just temperature or dissipation as a function of variations in temperature and depth. And that's something we measure as well. So like Andrea talked about, and we will see in the way that we measure turbulence in the mod labs with the microstructure profiler. That profiler kind of descends in depth, and it's both recording fluctuations in velocity. So that's the shear probe that Andrea talked about. You also have a sensor that's measuring fluctuations in temperature, and that we use this idea to kind of compute dissipation temperature variance, which is called pi, from that. Any questions? It's sort of very similar to an idea to what Andrea talked.
You can also ask questions about the previous part of the TKE equation, but the temperature variance and the TKE equations are derived very similarly. It's just that one is a vector, like one is one is a scalar and one isn't, and so there's a little bit more like messiness in the kinetic energy equation derivation. Yeah.
I have a question. I would be confused of once we assume an isotropy, we're saying for like the for epsilon. No, I just confused like how you get there's like a 15 and then there's a 15 over 2, right?
Oh
yeah, and I understood this. Somebody can explain it, that would be great.
Hard work figuring it out. We've been very confused about that one.
No, exactly. So I always be confused. So somebody can tell me.
Yeah.
It's the same thing also with temperature. So
yes,
yeah.
It's all so the derivative, if you can do it in for the kinetic energy one, you can do it for the temperature one as well. In fact, maybe we'll do that as a
The temperature one's going too though.
So, yeah, I was gonna say, so I think what I think makes sense maybe is I'm gonna do the derivation for how you get that that relationship of epsilon is equal to 15 over 2 nu whatever stuff. And then if you guys want to figure out how you get to the same thing for pi, that's easy, like something we can do afterwards and we can talk about it. Should I do this on here or on the board? Do you think we can do the board? Yeah. Well, the problem is that then the owl gets funny or whatever, right?
Let's see.
All right, let's give it a shot. Oh well. Where's that shot? Oh.
actually,
As the main thing, and then the owl is just
have to move it.
Yeah.
It's okay. So the question was, and what we were actually already going to talk about, so I'm really happy that you let us.
I don't want to like.
No, that was exactly it. I was going to say it since we still have time, because we weren't sure how much you guys had already seen and what you hadn't. I was going to go over where that comes from. So, right, it's actually somewhat straightforward, but it relies on assumption that that also has a separate whole derivation of it. So depending on how much time we can go into it or not. I also just do quickly want to mention, and something that we didn't say in the slides is there are different ways of writing epsilon. And again, this is all in the lecture notes, but you can also write it in like the strain rate form. So like, I don't know if you guys have seen it written differently, but you might have seen, we here we're talking about epsilon is equal to nu times e ui prime dxj and then squared, right? And you've probably also seen it written as let's see, 2 nu Sij prime Sij prime here. Has anybody seen it written like that? Or, yeah? These two are very related, so they're not exactly the same. Sij is defined as 1/2 of dui prime dxj plus duj prime dxi. It's in the notes. If you plug it into the equation, basically you just have to move around some of the terms and it ends up working out to be basically the same, and that's where this comes from. And they are slightly different. Like, so I called this one like epsilon s because these are both epsilon and they end up kind of being the same when you in terms of consequences, but technically they're not exactly the same expression. If you like did out the math, they don't quite work. You're missing like I think epsilon s is epsilon is like epsilon is minus a couple, like this term here, uy, uj, dxi, dxj. Now, sometimes you can kind of just ignore this term either because of assumptions about isotropy that allow you to like ignore double derivatives and stuff. And again, we can go into all of this, but I just wanted to point this out before I move forward, just in case you're confused. These are all basically the same thing. They're just written differently and you can move the terms around.
Andrea, there's
Oh, yeah.
Just if anyone didn't recognize, Sij is the string array tensor that we talked about.
Yes.
yesterday.
Sij is the string array tensor. So you can write it in terms of either one. Where's the eraser? In oceanography, we tend to like mostly use this top form, but in engineering, you'll use this bottom form. So you'll see both. But for moving forward, I will be using mainly the whatever it's called, pure shear form, or forget the term for it, but they're equivalent and I'll measure right up to. Cool. So how do we get to that 15? It's a good question, and it's something that's a bit confusing. Because you're like, okay, well, we assume isotropy and then 15. Sort of weird. Basically, to make our lives easy, we're gonna start with defining something that we call G1, just for my own peace of mind, which is gonna be du1 prime dx1 and then bar and then or not bar, like this thing 1 prime dx1 bar this guy. Cool, we're just calling it this so I don't have to keep rewriting it. So that's G. And then isotropy, what is it saying? It's saying that the gradients are the same in different directions. So if I is equal to J, we know that du1 prime dx1, or like this is really 4i is J. So the diagonals. I'm just gonna put squares here. I'm writing it like this. This is shitty notation. Apologies. Equals du2 x2 squared with a bar on it. Equals du3 x3 bar on it. That's all gonna be equal to G1. Does that make sense to people? Yes, we're following. That's kind of how we defined isotropy. We said that all the diagonal terms are related to each other. What about the off diagonals? Is the question. So this is the bit where I said there's a whole other derivation, which we can go into if you guys want. But basically, for when I is not equal to J, like if you're in the off diagonal terms, you end up with dui prime dxj squared bar equals to G1. I can explain where this comes from, but it relies on a little bit of like annoying stuff about defining a fourth order isotropic tensor, which we can do, but it's a little messier. So if we've established that every single off diagonal is 2 times a diagonal, and that all of the diagonals are equal to each other, we have to sum over ij, like there's an implicit sum involved, like you know your index notation, basically dui prime dxj dui prime dxj. This is an implicit sum because you have repeated indices. So that means that what you're doing here is adding up over I and j, all 3 diagonal terms and all 6 off diagonals. So you end up with, say epsilon is nu times this guy, right? So we'll get, nu times 3 times G1, these are the diagonal terms, plus 6 off diagonals times 2G1, right? So that's how many off diagonals there are and that they're equal to. You do out the math, that's 15. du1 dx1 1 dx1 bar. Yay, that's where the 15 comes from. The 15 over 2 comes from the same relationship, because if du1 dx3 is half of du1 dx1, then that's equivalent to 15 over 2 nu du1 dx3 du1 dx3. Because this is an off diagonal. Did that track for everybody? Yes.
Again, 1, that's 2G.
I didn't explain it at all, but I can explain it if you would like. All right, if this part good though, I will explain the 2G in a bit, but just, if this is true, does that work for everybody?
Like when you first coded in the slides, I thought it was like a more intuitive way of seeing why one was like half the other.
Yeah,
That's why I asked the question. I was like, oh wait, why is it like?
I was just explaining where this 15 came from first. The 15
Yeah.
comes from the fact that if you add up all of the diagonal top diagonals, you get the 15. This is definitely the
Yeah.
big thing, the hidden trick, which I can explain. You didn't seem super confident with what I just showed. Well, what's up? Talk to me, Andrea.
No, it's okay. I am just following because I understand that, for example, G is arbitrary. It's like like the G.
Yeah, it's not arbitrary. It's du1 dx1 du1 dx. But we just defined it that way, so I didn't have to write this in plain text.
So, and for that, that the numbers come from because you are aggruppated.
Exactly. But this is the real thing, right? This is the trick, because this all being equal to each other,
Yeah.
I'm saying this equal to this equal to this is equal to this. This is G1, they're the same term. And then everything else comes from the fact that these are all equal and these are 2G1. But your question is, okay, well, why is that true? G1 is like, why can we put everything in reference to this term? Is kind of the hidden assumption here.
Because it's entropic to the idea of the diagonal.
Yeah, so the isotropy says that these are all equal, so that explains this. What it doesn't necessarily explain as obviously is why the off diagonals be 2 times the on diagonal. Does anybody have like a guess for where that might be? Because I don't like have an intuitive explanation for that. Okay, I will explain it then, since Grant asked. Yeah, blame Grant when you get sad because I'm doing weird tensor notation, so. Does anybody know the general form of a 4th order isotropic tensor?
I have it in front.
Yeah, I have it in the,
Never just put it out.
yeah. Yeah, I didn't either, and I found this out when I was trying to figure out where this came from, so this was a rabbit hole I went down.
Yeah.
So,
Well, Sutano gave like this derivation as a homework question.
did he? I didn't get that as a homework question, you got better
No.
homework than I did. I love that. Wait, you've already derived it?
No, yeah, exactly. I was like, wait, I remember now when you were doing the tensor notation. I was like, wait, I did this like a few months ago, actually.
There you go. You wanna come?
Absolutely.
You'll be my assistant for this one. Has anybody else done this before? You did it.
But
So why do you ask the question if you've already done
God.
it? Okay, he forgot. Well, I guess I can remind you all. We're doing a homework question from Sutana's Turbulence class. I really hope I get it right now. If I don't, at least you guys have the answer.
yeah, exactly.
So, I mean, this is how it was written out. I'm not deriving this part. If this is what you guys derived, then I'm so happy for you, but I just take this as a given.
No,
Okay. C. I K delta J L. Take this as true. Because I can't go back any further than this because I don't know enough math. But this is one way of writing out this tensor that has 4 different dimensions in it.
but the tensor is isotropic. That's the assumption we're making. With using that formula.
Is that in the formula? I actually don't know. I kind of assumed this was generally true and then the assumptions of myself later, but I don't know.
Oh, I think it's the fact that you have the direct deltas.
Yeah, but that comes from a bunch of other places. You don't have to assume that. Every site that I found came up with the Dirac deltas, not assuming any kind of assumption.
I'm not sure.
Right, you can look up, there's all these math forums that talk about this, it's great, I didn't spend much time on them, but they explain where this comes from, I just didn't wanna understand. Okay, so, but then you make certain assumptions, so like, incompressibility. That tells you that T I K L is equal to 0. Just, I'm giving you a roadmap right now. This is gonna be a bunch of like coming up with systems of equations and then solving for that. Sorry again. So why is this true? Because if we have incompressibility, then dum dxm is equal to 0. Does that make sense to everybody? Yes, okay, great. So, I just pulled up m, but just to say like any kind of the sum of d velocity d distance is gonna be 0. That's how we defined it. Okay, great. So in that case, we can put that in I K L 0, which is a whole thing. Delta I. Does everybody know what a delta is here? Everybody know what that is? Raise your hand if you don't know what it is. 1 person, 2 people. Okay. Someone didn't read the index notation notes. But delta ij is the I guess Dirac delta is the correct term, but basically it's that it's equal to 1 if I equals j and equal to 0 if I is not equal to j. Cool. So let's keep going. You'll see why this is useful in a second. Delta I A delta I L. This is why I needed the notes because there's no way I was gonna remember all this. Okay. Because of the nature of the fact that like of like what delta ij is equal to, like it's equal to 0 if they aren't the same. So delta ii is obviously 1. We love that for us. And so for any situation where k and l are different, it's gonna be 0. So based on that understanding for all of these terms, you end up with delta KL times 3A plus B plus C. Because this is just kind of what ends up happening is you have this delta KL here, which could be, we're not gonna set K and L, but this is 1 because I and I are the same. These have to be true. You can move them around. I did the math out once. It was just kind of annoying, but you end up with this. And yes.
Sorry if this is just a handwritten question. The index is moved around from the top line where you find it to the line where one right now.
They shouldn't have moved anywhere. They're still at the bottom, I think. But if
Like they're still in all the same order.
oh, the order has probably changed. Maybe. I mean, I don't know. So the II is the same. No, they should be the same order. IK. IL. JK.
We just called DC.
Oh yeah, I think I just flipped around with B and what we see here. That was on me. I did this like a couple of months ago and it became a haze. So yeah, I probably switched them around. Anyway, yeah, I probably switched these, so we can probably switch them back and they'll be the same. I'll go back over it once I've done everything, make sure everything's consistent. Basically, because this is equal to 0, that means that 3A plus B plus C equals 0. Yay, okay. That means that we solve for B and C in terms of A. Sorry, actually, we're gonna do that in a second. I was skipping terms. We also know DUI, DXJ, DJ, DXI, bar, whatever. There's primes here that I'm not writing down, is equal to 0 for I not equal to J because of isotropy plus incompressibility. So this is where the isotropy comes in. I can again do out the math for this. It's just kind of annoying and just take my word for it for now. If you want to go over it after, I'll leave that as an exercise for the reader and you can come bother me afterwards if you can't figure it out. So TIJ or IJJI, I guess correctly, is 0. Delta B. C, which then gives you 3A plus 3B plus C equal to 0. Okay. So now we can solve for A, B, and C in terms of A. So, well, obviously A is equal to A, but A is therefore equal to B. And C is equal to minus 4. System stuff. Cool. Then after we've done all that, we can define G1 again, same way. So, you know, our G1 is again going to be our DU1, DX1, DU1, DX1 multiplied together, same as we did before, which is the same as writing it as T1111, right? Does that make sense, everybody? We're just plugging in the definition. And so that is equal to A delta 11 delta 11 plus B delta 11, etc. It's all delta 11s plus C delta 11 delta 11, which obviously is just A plus B plus C, which then is equal to minus 2A because of our understanding of how they are connected to each other. So if we plug everything in and we solve in terms of G1, we now get A equals B equals minus 1/2 G1 and C equals 2G1. Okay. Great. Can I erase this part? Is that okay? Wish I had one of those fancy sliding boards that gave you extra space, but unfortunately we don't have that. So now let's look at D1 DX3 B1 DX3. That's going to be T1 through 3. Right? Is our definition our answer? A delta 1,3 delta 1,3 plus B delta 1,3 delta 3,1 plus C delta 1,1 delta 3,3, right? Which is going to be equal to C, which is going to be equal to 2G1. So we're basically done because we now have T1313 is equal to 2G1, which is equal to 2T111. So we have D D1, dx3, D1, dx3 is equal to 2 times D1, dx1, D1, dx1. You have found the relationship between the off diagonals and the diagonals.
Which is not something intuitive.
It's not intuitive at all. Well, you knew that because you already took the class, but.
Well, no, but I don't remember this action.
Well, yeah, maybe it wasn't clear why, but this
Yeah.
whole thing, it seems like a lot of work for a fairly small relationship, but this ends up being important because if you understand the relationship of the off diagonals to the diagonals, now you can actually use isotropy, because if you don't have that relationship, isotropy is all well and good, but what are you supposed to do, right? Like you need to have the relationships off diagonals. So,
Well, also, I just did some research. I think the way you write a fourth order tensor, you're assuming isotropy there.
is this something, okay,
Yeah.
there you go.
Otherwise, I don't think there would be such a neat way to write a
That's
fourth
fair.
order tensor. So I think you're already using it since the beginning, and then
All isotropic, yay. Cool. Okay, I believe you, I don't know.
that's what people on Stack Exchange do.
Okay, I trust Stack Exchange. That sounds right to me. Anyway, so that, again, it's in the notes and I'll make sure that the order of the indices is correct, because I guess I got it wrong, but, that is how we eventually, we did all of that just to come up with that, like, off diagonal relationship to the diagonals. And then once you have that, you can relate all of the terms together, and that's where that 15 and the 15/2 kind of magically appear. Yes. Seeing a lot of faces that are like, why did you make me do all that math? And as I said, blame Fran. We still have, what, 2 minutes? Do you want to do the?
I can speed run ready to.
No. Sorry? Oh, Eddie. Oh, yeah, you had
That's
that,
the
yeah.
only thing.
Okay, yeah, we have a couple more slides left. Sorry, we took that break, but.
Oh, is it already break?
No. I said,
Okay.
sorry, we took that break.
Okay.
As in, we took a
already-
break.
I see.
and indexation.
What class was this?
Yeah, the MA.
Oh.
Oh, I thought you were asking what class you were in right now. I was like, oh no. So loud too. It's like,
Yeah.
you're not paying attention.
The MA program.
Okay.
Should I plug in the owl?
Yeah.
It should be already collected. We just have to.
Yeah,
switch.
Oh, okay, yeah.
Grants and activities. This is actually our second tour. Class together. Yeah, exactly, together.
Great. And then share screen again.
That's just like, I want to teleport myself out of here. I'm so fun doing this homework for your question, for example, we trying to explain to Grant and distance. Just gonna get sentences there. Ooh, that was getting really flat.
And hopefully all of that math saves me the trouble of explaining why
Yeah.
this is the case, because this one is a. Oh, the lights. Thanks, Amy. So temperature, not as complicated, not as many dimensions, but same idea. So
Sorry,
Yeah.
shouldn't there be like an X1 in the middle? Like they seem kind of the same. Like whatever's on the left hand side and right hand side of the equal, the last equal sign. This is.
Yeah, there's a 3 times 2, which is 6.
yeah,
Oh, okay,
yeah, this is it.
but is it a 3 squared? Just, I don't.
Oh, yeah, I'm not, I think it's just unfortunate notation. I think she meant to write
Oh,
3
oh, okay,
I'm sorry.
times dt
That is
prime
right.
dx3 dt prime
That
dx3.
is right.
No, I thought like
That's
even
my
for
fault.
what we did, like.
No, you were,
Oh,
it's
sorry.
that there aren't really off diagonals in this situation
exactly.
because temperature's a scalar. So you end up with 6 du instead of,
Yeah.
it's,
Yeah.
I think you just need to rewrite that
Yeah,
equation. I
I'm
think that-
sorry.
Yeah.
That's okay.
That was a typo.
Make sure that I didn't.
It's a good question. You caught something.
I will correct that in the notes. That's from the notes. There we go. Okay, so this is going back to our kind of momentum equation. And this, Andrea talked about this a little bit in the mean flow momentum that she did, the mean equation for momentum.
This is doing a similar kind of eddy diffusivity for turbulent quantities. So in this case, we just think about three terms. So we're just thinking about the terms that produce turbulence. So that's buoyancy production, shear production, and then the terms that drive its dissipation. And you can rewrite this buoyancy production term in terms of stratification. So that's just kind of rewriting it as a buoyancy gradient. Yeah, and this one, I can rewrite this. This is not the easiest way to, that was not the easiest way to see it. See here. So what this is basically saying is that and if you take negative G over naught, or negative G over rho naught, you get buoyancy. Yeah. Oh, sorry. This is kind of a similar idea to what Andrea talked about, right? You're taking kind of nonlinear term and breaking it down as a gradient with some constant diffusivity. So similar idea, but now you're kind of thinking of turbulent fluctuations in velocity. So this is the turbulent component of velocity instead of the mean component. So now if you define a term called the mixing efficiency, which is just the ratio of this buoyancy term, now we're thinking of it in terms of how much turbulence is produced through shear as a ratio of how much is lost through changes in buoyancy. So that's what this mixing efficiency term is telling you. And plugging that in, here you can kind of rewrite this equation in terms of this mixing efficiency. And if you kind of take these are all just sort of defined, but this equation basically rewrites to this equation here. So you can do the math. I think I did it in the notes, but if you do the math, it will just give you back this equation here. And typically, we tend to assume a value of 0.2 for the ocean. Oops. And that gives you a sort of parameterized eddy diffusivity using our epsilon values. Does that make sense? It's a little bit of hand waviness. We're not actually doing out the math, but it is literally just looking at the balance of these three terms and coming out with and making an assumption of how efficient mixing is in the ocean, and using our measurements in epsilon to get to a diffusivity, eddy diffusivity.
So is gamma, capital gamma, the affecting the eddy diffusivity?
It's not kappa, it's like a coefficient that's based on mixing efficiency.
Oh.
So it's how efficient turbulence has been in changing buoyancy, which is really changing the density of the fluid. And this is a term that there's been a lot of recent work kind of trying to understand whether this is actually constant or whether there's a lot of whether there's depth variability to it or if there's regional variability. So this is definitely an assumption that we're making and may not necessarily be a great one for the ocean, but and that's just kind of a way of getting to a term like this, which we can then put into models and things like that. You can do a similar kind of argument for chi, which is the temperature variance, dissipation of temperature variance. So you can also get an equation for any diffusivity of temperature variant or any diffusivity of temperature.
And this is any diffusivity of buoyancy. Just kind of assuming that the turbulence processes that are kind of changing momentum are also kind of changing buoyancy. That's kind of that main assumption there. Generally, and this is something we'll discuss a bit more, we kind of assume that what's driving changes in buoyancy is also driving changes in temperature. And so that's typically assumed to be equivalent. And if you do that, you can get epsilon from values of pi or vice versa, but it's typically used to get values from pi. And this is stuff that if you're familiar with work like Jim Moon's work, they have all of these instruments on moorings called pods that measure temperature, dissipation of temperature variance. So this is a way of getting to this dissipation from that. Any questions? And yeah, we will actually get to do this with our measurements because we actually have both of these and we can compare and see how and see whether how comparable the diffusivity of temperature and buoyancy is, which will be an interesting experiment. Okay, so we made a lot of assumptions to get to where we got to. And so some of the main ones were we assumed isotropy. So Andrea did a great job of kind of explaining how the math worked for that. But that is an important assumption in how we actually get to getting dissipation from measurements. We just kind of have to assume isotropy. The other thing we assume is also that there is a large scale separation between things that are between the processes producing turbulence and how it's dissipated. So that's sort of that we're able to get that full energy cascade that Charlotte described. And like Charlotte talked about, it's not necessarily the case that, you produce energy at large scales and it sort of cascades into smaller scales. You have all of these processes that can also cause dissipation at different scales. And it's not just a sort of linear change. And that is another kind of area of research that we're still working on. And then to get to eddy diffusivity, which is kind of to be able to compare measurements of diffusivity of temperature to buoyancy, and kind of see how turbulence is driving changes in both gradients in temperature and buoyancy. We tend to assume a constant mixing coefficient that comes from this idea of this constant mixing efficiency. And another thing that we do is also assume that diffusivity of heat and salt are the same. So that way we can say that this is the same. Yeah, so that was the conclusion of our lecture. We went a little bit over time, but these are terms that you all are going to see a lot over the next 2 weeks. So we wanted to make sure you understand all of these stuff. So when we say something like epsilon, we say pi, we say eddy diffusivity, are those kind of terms that people feel like they have a good grasp of? Yeah, any questions? Any questions? Yeah. And yes.
I don't feel like I have a good understanding of epsilon chi. Yeah, I would say those two and the mixing coefficient.
Yeah, so
That was a goal. Or if you were asking us.
yeah, no, it's a good question because
I was gonna say, maybe it'd be a useful exercise as a group to just like go over and put words onto like, let's define epsilon, let's define pi, let's define viscosity, thermal conductivity, and so you're mixing efficiency with mixing coefficient. Just like do that as a little verbal exercise. We do that right now, do it during break.
Well, it is the break, so same thing.
yeah, actually, that's a great idea. Yeah.
What about epsilon is like not gelling?
I mean, I haven't seen it before, especially with those equations, so I'm just not used to that term in there, so.
Right.
But like the concept of diffusion of turbulent kinetic energy. Is that what's,
The
Sticking?
diffusion of turbulent kinetic energy. Yeah.
basically, yeah, it's how much, it's when you keep going downscale. It's like the way of thinking about it, the simplest way, is like things move, they transfer some of that momentum to things that are even smaller. To things that are even smaller, things that are even smaller. Once you get to a small enough scale, the point at which we will discuss in the next hour, past this defined scale, it can't transfer to smaller scales of energy because motion at that point is dominated by viscosity. So what ends up happening is that instead of just moving energy down scale, the wiggling is just gonna dissipate away into. And so that's what epsilon is representing. It's representing how much of that, it's representing the kinetic energy. Again, if you think about it as like a budget, that equation is a budget, right? So you have like control volume, in, out, whatever, and then in, out, moving around, created, and death. And so epsilon is the death of the turbulent kinetic energy because of viscosity. So when you're in a scale small enough that viscosity is dominating the process, it eats all the energy basically is giving you.
Interesting, okay.
And like I said, the reason why it's like a useful thing to think about in a lot of ways, because you can, or rather, there's an assumption made that basically if the amount of energy is like the same across the cascade. So if you know how much energy is being dissipated into heat, then you know kind of how much energy is being transferred at any given point. See, if energy is conserved throughout the whole cascade, all the scales.
No, that makes sense, yeah, I think that makes sense.
And it's similar with chi. So in the case of chi, it's more like these turbulent processes are, like the idea of strain and shear, they're sort of straining and creating these sort of gradients in temperature. And that those gradients drive diffusion of heat, which is a bit more intuitive than diffusion of momentum. But it's a similar idea with chi as well, sort of a dissipation of all of these sort of gradients that are created by turbulent processes.
But the diffusion of heat is diffusing into what? Just spreading it out?
It's going into molecular processes.
Okay,
Yeah, so it's going into like making molecules move much faster or
Okay.
there's like,
we mean that it's going into wiggling molecules instead of wiggling parts of water.
but you're taking it, so I like cause you're taking it from momentum or kinetic energy, right? And then that makes sense to me that at certain scales, because of viscosity, you can no longer move it into kinetic energy, so then transform into heat. That makes sense to me. But then the chi term you're saying is taking heat to heat or
Temperature is not the same as
Temperature.
heat.
okay,
Temperature is a, a measurement of like this, again, temperature and heat is a confusing thing, but basically they are related via the like heat capacity or whatever. So when you have temperature can change across scales, but at a certain point, it's that the temperature is going into generating heat rather than just changing again, the problem is our language is horrible for this. Rather than heating up, rather than changing the temperature of different scales, it is now going into heat. So temperature and heat are not the same thing.
okay.
yeah, the idea, and it's not temperature, right? It's temperature variance. That's the quantity that we're looking at. So this is a kind of an Helmholtz example, but it's like you have instabilities in the ocean that are causing like these layers to stretch and strain. So the turbulence is kind of forming features like this, for example, and then it's the diffusion that's kind of smoothing out the gradients. So the temperature variance is described by this, and then the dissipation of temperature variance is what's diffusing out to kind of smoothen out the gradients.
Okay, for that, okay, that makes sense, thank you.
Good question.
Yeah.
Any other questions?
I don't actually remember if you guys are gonna talk about this on right in the next lecture, but can you comment on like, so you talked about how kappa rho would be assumed is equal to kappa t. Can you comment on like how we plan kappa, like the additive of momentum?
Yeah, so,
Sometimes we also assume it's the same thing.
yeah, so the eddy diffusivity of momentum comes from, this idea that, and I will remove buoyancy, because I feel like buoyancy starts confusing people. But this is the general idea, is you have a turbulent process that's, and this is a fluctuation here, so in our notation, we don't use that, but this is a velocity fluctuation and density fluctuation. So you have a turbulent process that's like driving a change in the location of a parcel of water of a certain density. And then you can think of that as smoothing out gradients again. So if you have a gradient in density, the eddy diffusivity gives you a sort of estimate of what mixing does to smoothen out the gradients in density. So that, but you can use a very similar idea and do that for temperature as well. So if you have so yeah, you can do a very similar idea for temperature, that the turbulent processes are then smoothing out gradients in temperature. And we can only really make this assumption if, say, you have something like a shear instability. In that case, you're mechanically moving fluids of water. And so you can then say that, oh, whatever turbulent process is driving this homogenizing of density is doing the same thing for temperature. But in a case, and I talked a little bit about this, but we'll talk about it a bit more later on. But in the case of something like double diffusion, where there isn't really a shear instability or a gravitational instability, it really depends much more on what the diffusivity of temperature and salinity is. This becomes a lot, this difference between these two terms becomes a lot more important.
I think what Kaiki was also asking about was if there's a diffusivity for momentum.
Oh.
That's what I discussed yesterday, which is the parameterization that I did for the Reynolds stress discussion, you recall?
Yeah.
That like A sub B, that was the same thing.
Yeah. But just so like the idea of the Pareto number stuff that the ocean, like these things are obviously not the same, kappa rho and kappa D momentum, density and diffusivity, but sometimes we just assume it's the same. It's as best as we can.
I would kappa rho and kappa T. We don't usually, we don't usually talk about, when we're talking about mixing, we're not usually talking about, the way that's related is via the energy equations. We don't usually bring the momentum equation into this. So that's why we have epsilon in this discussion, but we don't have like the eddy viscosity. Because I mean, brother, it exists as a term, but I don't think we ever assume that kappa rho is equal to AB or something like that. That's just not an assumption we make. This is an assumption we make. Yeah.
Sure. Yeah, not sure if you fully answered that, but
I think you could.
Yeah.
Also, you're not meant to be trapped in here.
Yeah.
It is your break. If